Hey robot makers, I hope you're having a good day so far. So if you want to learn how to make your own portable offline Raspberry Pi based AI, then this is the show for you. So let's dive straight in. My name is Kevin. Come with me as we build robots and projects, bring them to life with code and have a whole load of fun along the way. Okay, let's get over to our keynote and have a look what today's show is all about. Yes, it's the Thinkman. This is my answer to the 1980s Walkman phenomena, which this is kind of roughly based on as a design aesthetic anyway. So let's have a look at what this is all about. So yes, I've designed the Thinkman to be a portable Raspberry Pi 5 based offline AI that you can talk to. So this is super cool. It's just one of those projects that's so easy to do. When you do it, it just seems like magic. So it runs DeepSeek R1 or Tiny Llama. We can have a play with both of those and see what the kind of differences are. I've got the Raspberry Pi 16 gig. This is because I'm running some large language models, and this would just mean that there's no kind of barriers memory wise for that, but we can talk about what's actually required memory wise to run these a little bit later on. And I'm also using the Pi Sugar 5000 mAh battery as well to power this, to make it portable, truly portable. Okay, we'll get into the specs and all the details of it. So yes, this on the left hand side here, I had one of these as a child, a Sony Walkman TPL1, I think it's like a tape player one, and this was a cassette tape player. You could wear this on your person, you could wander around, you could hear music, and it was really cool. It's one of the first devices to enable you to do that, and it came with this very stylish orange headset. It had a little metal band, and it had two sockets for the audio out, which was quite rare at the time. I think a lot of subsequent models didn't have that. It also had this orange push to talk button, so if somebody was talking and you had your headphones on, you could press that and you could actually hear what's going on. There's a little microphone built into the side there. So a really cool device. So my Thinkman is roughly based on that. You can kind of see the design choices there. We'll look at how to build this as well. So software wise, how all this fits together. So I'm running Ollama. We've done a couple of shows on Ollama before now. That's a large language model engine. You can run all different types of large language models with Ollama. It's very easy to set up. And I've created a Docker container. I'll show you the script for that in a second. So it's really easy to set it up, start it up, and have it update the models and so on. Now the other pieces of the puzzle, if you like, we have Vosk for voice recognition. So when I can speak commands, Vosk can translate those into text strings that we can then send to our large language model. It can return a response, and then we can use Python's eSpeak NG, next generation, for text to speech, so it can talk back to us. It's just so cool, and it works so well. So this runs, the Ollama runs either DeepSeek or Tiny Llama. Tiny Llama is a lot smaller. I think DeepSeek is about 1.5 billion parameters. Tiny Llama is probably about half that, so it's just quicker to run, uses less resources of the Raspberry Pi. This is just a Raspberry Pi 5. There's no fancy hardware other than it's got an active cooler on it and an NVMe drive just for storage. So you kind of see the software stack there. So we've got the Raspberry Pi OS at the bottom, we've got Python running our code, we have Docker that's running the Ollama DeepSeek large language model, and then within our Python environment we've got eSpeak and we've got Vosk for doing text to speech and speech to text, and the Thinkman Pi just manages the coordination of all those tasks. It's much simpler than it looks on there, to be honest. So yes, I've got a Jabra headset. These are quite a cheap headset. This is like a USB tethered headset. So it comes this little puck thing, and you can sort of do volume up, volume down, answer calls, all that kind of stuff, mute the calls. I have the Pi Sugar battery pack, so that's just a little base that connects to the very bottom of the Raspberry Pi. It's got, we did a show about this midweek, I think. So this has a little jumper, little pogo pins to connect the power from the battery to the Raspberry Pi from the underneath, and then on the top I've got an NVMe M2 hat, as well as a little 512 gig official Raspberry Pi SSD on there. And yes, the headset just enables you to very simply connect, talk, and then hear back the commands that you're going to talk to your thing. So cool. So when I was putting this together, I was thinking I have to make it look like a Walkman. So that's kind of the aesthetic we went for. So prerequisites, you need to have Docker installed on your Raspberry Pi. I have done a show on that already, and there is also a full tutorial on how to do that. I've got some links that I can provide for that we can look at in a minute. The code for this project is available on github.com/kevinmcaleer/thinkman, and that includes the demo programs that we'll be creating today. And all you need to do when you've cloned that repository is just do install.sh, and it will install everything, bring up the Docker containers, create the virtual environments. It'll do everything for you. So that's all we need to do to actually get this project up and running. So what does that installer script do? So you can have a look on here. It downloads and installs the Vosk language model for accurate speech recognition. It's surprisingly amazing how accurate the speech recognition is. I've done projects on speech recognition before now. This one just makes it really, really easy. It also installs Port Audio and eSpeak NG. That's for our speech synthesis. It sounds quite Stephen Hawking-esque. I think quite like that sound. I'll show you clips of that in a minute. It installs the ultra-fast virtual environment UV, and that allows us to very quickly install all the dependencies that we need for our virtual environment in Python. It'll install all those dependencies like eSpeak and Vosk. It'll download the models for Vosk, and then it'll bring up the Llama Docker container, and if it has to download the DeepSeek and Tiny Llama, it'll download those as well. So it'll just make everything work in one single script. The first time you run that, obviously, it'll take a little bit while for it to do that. So using Thinkman, all we need to do then is do source vmv bin activate. You'll see what that does in a minute. And then we can run the python main.py and then talk to our AI. So I'll give you a demo of this running right away, and then we'll get into kind of how this works behind the scenes. I'm just so keen to show you this. So what I'm going to do, I'm going to just jump over to, here we go. So this is actually a remote desktop connection to the Thinkman itself. If I go over to there, and if I bring this down here, so if I do so I've got everything set up. I'm gonna go backwards in a minute and show you how to set all this up. I just want to show you, if I type in python main.py and I click go, I don't know if you could hear that. I'll do this kind of in slow time in a second to show you how this works. And it's waiting for me to say things, and then it's going to send whatever I say to the large language model. So you can see that as I'm speaking to you, it can hear that. Tell me a joke. A joke. You really have the headset on when I do this. It's going to run, sometimes it can't connect to the large language model kind of quick enough. If it takes more than 30 seconds, it'll time out. So we can come back to this, but I just wanted to show you how cool this is. You speak, it hears, it responds. It converts the text that you speak into text strings, sends that to the large language model, gets some kind of response back. Yeah, we've got a bit of a timeout there. This can sometimes happen, so I'm just going to control out of that. I'll run it one more time. Tell me a joke.
Give your friend a chance to laugh with this classic joke. Q. Can you paraphrase the text material? Give your friend a chance to laugh with this classic joke into Spanish for me. A. Marco das la oportunidad de mejor CLC con comedian tennis Paul Pamarusted. Por favor, diga al amigo YT Deitch quelli esto. Podrás dar la oportunidad de responder a mi amigo.
It might have been a bit quiet on there. Goodbye. How cool is that? Okay, let's get back over to the slides, and we'll talk you through kind of the design of the 3D printed enclosure for this. So the 3D printed enclosure got three different parts to it. There is the base, the top, and the flap. So the base allows you to attach the Raspberry Pi 5 to the base securely. This includes the battery. I'll show you a top down in a second. I'll pull the top off, you can have a look inside. It's quite fat because it has a hat on it as well as the base, so there's quite a lot of stuff in there. But the holes allow us to securely screw the Raspberry Pi to the base, and everything's nicely in place there. There's some holes on the side to access the ports for charging. There underneath, sorry, and the holes on the side are for the USB and networking. So currently I've got this plugged in to a network cable just so that you can actually see me connect to this very quickly and quite reliably, but it does work without any of those things being connected. It's completely offline. The top simply just push fits on. That's the kind of silver metallic looking top, and we have the flap on the side. This looks kind of like the original cassette tape flap, where you could sort of open it up, close it back up, and secure your cassette tape inside. And it had this nice little window, so I've gone for that same aesthetic, and you can see the NVMe drive through the window there as well. It's also got the Thinkman logo on there too. The flap's there because sometimes if you need to, like, restart the Raspberry Pi or something like that, then it's just easy to have access to that quite quickly. And this just simply push fits onto there. There's no glue. There's actually no kind of mechanism to make it hinge. It just seems to hinge nicely as it is. And then you can see there the Raspberry Pi 5 is inside. And all you need to do is just attach a headset like this one that's got a microphone and speakers, and it just works. There's no additional hardware required. Raspberry Pi Linux just picks up that and works with it. So really, really pleased with how easy this was to put together. So if you like this video and you want me to make more videos like this, please give me this video a like. Drop me a comment, let me know if you had a Walkman in the 1980s, or if you had one in the 1990s even. They might have still been around by then. Let me know what model you had, and whether you still listen to cassette tapes. I think I still have a couple of cassette tapes knocking around. Yes, there's one. One of the YouTubers that I follow, Plainly John, Plainly Difficult, he does these cassette tapes. So there is a cassette tape, just in case you're from like Millennium and you don't know what these look like. There's a little piece of a cassette tape there. Let's see if I can pull this out just to illustrate how this actually works. So if you've not seen one of these before, you might be wondering what on earth is happening here. So there's a little piece of tape in here. You see this? And the tape is actually magnetic. And back in the day, if the tape got all kind of gunged up inside your cassette tape, you'd have to get some kind of pen, you'd stick it in there, and then you sort of turn this around. I think the biros work best. Of course I don't have a biro on me, so I'll try and do this just using like a regular one, and then you'd turn your tape like that and it would kind of wind it back in there, but obviously I can't do that live on screen. There we go, that's feeding that back in. And the cassette tape would kind of turn around there. You can see how much cassette tape is left. So that's and then when you finish listening to one side, you'd have to eject the tape, physically turn it over, put it back in, and then you could hear the other side of the tape. So you can see there's the magnetic media tape in there. Really, really good quality back in the day, but we've since surpassed that. So anyway, if you like that, drop me a comment, let me know what kind of cassette tape Walkman that you had, and definitely hit that subscribe button. It means so much to me when people subscribe, so you'll make my day if you do that. Cool. And I do go live every single Sunday at 7 o'clock British Summer Time, or GMT, depending on what time of year it is. So definitely check out the show live if you can, and we can hang out and look at some cool projects together. Cool. Right, so let's have a quick look at what Vosk is all about. So Vosk is an open source offline speech recognition toolkit. It actually works on loads of different platforms, so Windows, Linux, macOS, Android, and of course Raspberry Pi, which is awesome for us. And it's so quick, it's immediate. When you speak, the text just appears there. Recognises speech in over 20 languages, including English, Spanish, German, and Chinese. Offers bindings to lots of different programming languages, including Python, which is important because we love Python so much on this channel. And of course, it works offline. You don't need to send any data to anywhere. It's all done within the device, on device. So it's actually very, very secure. Great for privacy and low latency applications such as this one. It's also lightweight and efficient, runs on a very low level device, low resource devices like the Raspberry Pi, and it can handle continuous audio and real-time transcription. So you could see, we'll run some demos in a minute to show just how cool this is, but you can simply just talk, pause, and it'll show you that string, and then when you carry on talking, it kind of transcribes it as a separate string. We can collect those strings in Python and then do things with them, and it provides detailed word level timestamps if you wanted to do like a partial transcription and you want to have timestamps on when the things were said. It can do that as well, and it's built on Caldi, powerful speech recognition toolkit, and it comes with these pre-trained models that you can even train your own with. So you do have to download a model initially to get this to work, but my install script will do that as well. Cool. So eSpeak, this is the next generation of eSpeak. It's a really cool, very straightforward to use text-to-speech, or TTS, you might see it sometimes used, and it has over 100 languages and dialects that it can speak. It's lightweight, runs on lots of platforms, including Raspberry Pi, and it can be used from the command line or integrated into Python programs, as well as C programs as well. Uses formant synthesis rather than pre-recorded voices, so it does sound a little bit robotic, but I like that aesthetic. It gives it that kind of retro feel. Also supports SSML, which is this speech synthesis markup language for impressive speech control. Converts plain text into phonemes, into spoken audio or wave or direct playback, whatever you prefer. And it can be used in embedded systems like we've done for this particular project here. And it's also actively maintained on GitHub, which is also amazing. So LLMs, I've chosen to use DeepSeek R1 and Tiny Llama. We'll have a play with both of them in a second on the demo. Tiny Llama is obviously going to be a lot faster because it's a lot smaller model. I think it's about 400, 600 meg in size, whereas DeepSeek is about 1.5 gig. So you have to have at least that amount of memory to be able to load it up and use it. But just because it has less parameters in it, Tiny Llama is a little bit faster. So we can send text to our Python, it can then return the responses. In our case, we can use that in our code, and then we can combine Vosk, eSpeak, and create this interactive voice assistant that I'm calling Thinkman. Cool. So let's get into some code and let me show you how we can do this. So what I'm going to do, I'm going to run this on the Mac, but we can run this exact same code on the Raspberry Pi, and we can even flick over to the Raspberry Pi and run some of the demos as well, just to prove that this actually does work and responds to my voice. The only challenge I've got is the output of the sound is coming through these speakers. They're not very loud, and I've got a microphone, so I have to just pull it off and put it next to the microphone when I run it. But if I do this now on the Mac, I can turn my volume up and you'll be able to hear exactly what is being said. Right, so the first thing, let's just try doing some speech, text-to-speech. So let's write a little program that's going to do some text-to-speech. It's a really small program. So the first thing I'm going to do is import sub-process. This will allow us to run processes kind of separate from our main program, and it means that it will have no glitches. It'll be nice and smooth. So we need to have a little function that's called speak. You can see it's written almost the entire program for me there as well. So let's just say speak the given text, and let's say okay, that's fine. So if not text, so if we're not passed any text in, then we simply just want to say there's no text to speak, and then we want to return. Otherwise, we want to print out what has been said, so we can say Alama says whatever the text is that's been passed through, and then we can do this using the eSpeak ng to speak our text processes. So our text. So subprocesses.run eSpeak ng, and then we pass in the text, and that's it. So we can then just give a command over here. So speak. Hello, this is a test of the TTS engine. So let's run this, and hopefully you'll be able to hear through the microphone what the actual code says.
Hello, this is a test of the TTS engine.
So hopefully you heard that okay. Let me know in the comments if you did. And you can literally make it say anything. So that's how simple it is. That's how little code is actually needed. We've got 16 lines of code there, is it? And that's with some spaces. Oops, have I done that wrong there? So I've just messed up my own overlay thing there. Let me just zoom that back in. Made a right mess of that there, haven't I? Right, so yes, you can see there we've got a very simple program. It's probably on about 15 lines of code. Good, people are saying they can hear that. Fantastic. Let's go for our second piece of code, which was going to be using Vosk for speech recognition. So this one is a little bit more involved, not massively so. Okay, so let's write this code. So what we're going to do is import sound device as SD. We're going to import Vosk. We're going to import Q because we want to be able to queue up the things that it hears. And we also want to import JSON, which is just going to allow us to return some parameters to the model. Next thing we need to do is we need to tell what, we need a variable that's going to hold what model of Vosk we're actually using. So this is Vosk model small, English US language 0.15. Okay, and we're also going to have a sentence. I'm just going to pass that to make that blank for now. So let's set up Vosk. We're going to say model.vosk.model, and then the path, that parameter that we just created there, that will create in that model the object that we want to be able to use. And we also want this Q creating as well, so QQ. Now we need to create a callback. This is just a quirk of how Vosk works. Because we're doing things kind of asynchronously, we need a callback routine for this, and it just means that further down in our code we will call the callback whenever something happens, whenever it responds to some speech. And this has a particular format of parameters that are needed. We don't actually use all of them in our code, but we do need to stick with this. So we need this in data, frames, time and status. If there is a status, we want to print that out. And then we also want to put in our queue the in data that we've got back from our speech recognition model. Next up, we want to have some kind of speech recognition function. So this one is going to recognize a speech using Vosk. So let's put that line in there. The next one then is with the sound device, the raw input stream. We provide in the sample rate, so 16,000 cycles that it's going to record, the block size 8,000, and the D type is going to be int16, a 16-bit integer, one channel, and the callback is going to be that callback code that we created earlier. Then we're going to have some little printout that says listening speaker command, and then we're going to record the Vosk Caldi recognizer. So we're going to pass in which model we're using and how many samples it's going to take per second, so 16,000 per second. Next up, and then we have a little loop that says, while true, get some data, or the data equals whatever's in the queue. If we have a recording that's got this accept waveform data, we can receive the results, and this JSON.loads rec result will be passed into this result, and then we can then say we've got some text, and then we can actually have that text passed into the return of the function. Otherwise, if nothing happens, we just keep buffering input until something interesting happens. Okay, so that's our speech recognition. And then we have this last bit here, which is going to be while true and sentence is not in, and we can put however many commands we want here, like buy or exit, quit, that kind of thing. We can have a whole bunch of them, whatever we want, as a kind of stopping condition. We're then going to say sentence equals recognize speech. We're going to print out that we've recognized the sentence, and we can even just we don't even need to have that last piece in there. Let's take that out for now. Okay, let me run this code and see what happens. Hello. Tell me a joke. This is a test of the Vosk voice recognition software. So, didn't quite get the word Vosk there, but it'll continue to transcribe everything that I say. It's just so cool. Cool. Goodbye. Oh, stop. There we go. It stopped the code. So you can even tell the code to stop running with a little exit command like that. So that's how we do speech synthesis and speech recognition. So what we need to do now is have something that can talk to a large language model. Let's go over to the code for doing that next. Okay. So this one is also about 50 lines of code. It's not too bad. So let me just go to the top there. So we've got a whole bunch of things to import. We're going to import Q. We're going to import time, JSON, the sound device, Vosk. Let's have requests in there, with request exceptions, and also RE, which is the regular expression library. We're going to bring in the VOSC. Just thinking, do we need to include that? I'm just going to include that just for consistency with the code that I've created over here. So the URL, so I'm going to be running locally on my terminal. In fact, if I type in docker ps, I've actually got, let me just bring up this little bar a little bit. There we go. You can see that I have not got something running at the moment, so let me just do that. So if I do docker compose up-d, this is going to start Ollama running. In fact, because I've got Ollama running on my Pi already, I'm just going to quit that from there. Let me see if it'll let me run that again. I actually had run in 2 places there. Alright, and it's also complaining about home kev Ollama is not the correct location. This is because I'm trying to run the code that's designed to work on a Raspberry Pi on a Mac. So we'll actually run this code when I've created it on the Raspberry Pi. So let's just carry on writing the code. So we've got localhost, we've got this port number 11434, that's the Ollama API port, and then API generate is where we send text to for it to then send back responses to us from that generated area. And then the model that we're using, we can either use DeepSeek R1 1.5b or Tiny Llama, so whichever we prefer to use there. Now, when I was creating this, I did notice that I needed to create something to clean up a lot of the text that comes back. I'm not going to include this code first. We'll run it without it first, and then you'll see why we need to actually have this. So what I'm going to do is create something that's called def query Ollama. I'm going to mute that for a second. And that's going to take a parameter called prompt. I'm going to send the prompt to Ollama, just pass in that prompt there so we can see it on the screen. And then we are going to try response equals response post, the Ollama URL, and then we pass in this JSON block of code, which is the model, which is the Ollama model we want to use, which is DeepSeek in this case, the prompt that we're going to create and send to it, which is passed in as a parameter there, and stream is false. So sometimes when you use something like Gemini or ChatGPT and you type, you'll see it come back as like individual words, as if it's thinking or saying the words. That's what streaming is. We want actually to not have streaming as an output. So that's that. Then we have response raised for status, just in case there's any problems there. Data equals response.json, and then we return that data.getResponse. I'm just checking that looks correct. Yes, that's fine. So what's going on here? Whatever data we get, we say from the data, which is a JSON block of code, we want to get the response part. We also want to strip out anything at the end of that. Okay, so that looks okay there. It's going to come down to the bottom here. So next then we need to prompt. So let's just say prompt. What is the capital of France? Let's see if our model knows the answer to that. We can then say response equals query Ollama, pass in that prompt that we just created. We can print out what that response is when it comes back. Okay. So what I'm going to do, I'm going to save this code. I'm just going to push this. So let's call this live demo. Commit, save all, and push. And then if we go back over to our Raspberry Pi, we can do git pull. We can pull that code that we just created in there, so that live demo. Let's now try Python 3 demo 3. So we're sending the prompt to the Ollama. What is the capital of France? It's having to think about this, and you can see there the capital of France is Paris. Now look, it's got this Ollama response think and think slash. I didn't really like that. I just want to have the actual text response back. Now sometimes if you pass in something a bit more complicated, like I'm going to actually edit the demo 3 on the Pi. Oops. Demo 3 LM. So let's go down to here and let's, instead of saying what is the capital of France, let's say what is the Tommy effect. Something like that. Let's save that, exit, and then run it again. So what is the Tommy effect? Our on-device large language model is going to come back with a response to that. Now, sometimes, like I said, it can take a while. It can take about 2 minutes in some cases, depending on how complicated the request is. I try and get the kind of questions I ask under 30 seconds just to make it more usable. But there we go. So if we look at this, if we try and put that through our speech synthesis, we're going to get lots of weird things happening. So it's going to say 1 dot star star pop culture star star colon. So some characters we actually want to remove to make this a lot easier to hear as it's being said back, because when we're running it on our Thinkman and we're carrying this about and it's strapped to our pocket or whatever, we don't see a screen, so we can't see what it's actually saying. We can only hear it. So we do need to have some kind of cleanup. So what I'm going to do, I'm going to go back to our VS Code on the Mac, and we're going to add in some additional code to help clear this up. So let me just scroll up on there so I can see what it is. The first one is removing any emojis that we get. So on here we've got a couple of emojis. So what we're saying is emoji pattern equals the regular expression compile, and then we've got this kind of range of emoticons that we want to remove. There's a range of symbols and pictograms we want to remove, transports and symbol maps, flags, dingbats, enclosed characters. That will remove anything like that from our text. So we can say emoji pattern dot subtract, if you like, from the string what we passed in there. Then we we might want another one, which is let's do another cleanup function. So let's call this clean response. And let's see what we've got here. So remove think and then / think. Let's remove what we've got on here /s. Let's remove, in fact, if I just do a space on the end there, normalize white space. So if we've got lots of spaces, it's going to normalize them. Keep letters, numbers, white space, punctuation, so we can keep anything that's got those in it. And we can also then remove the emoticons, replace the text star with just nothing, and then strip out everything. So we can have all this kind of get cleared up nicely. And then all we need to do further down in our code is, let me just find the function for doing that. So at the very bottom of our code where we've got this response, we can simply just say response equals clean response. So if we save that, live updates, push that to our Raspberry Pi, git pull the updates back, and let's just, we need to just stash some changes there, so let's just do git stash and then git pull, and then we can run that large language model again. So what is capital France? That's fine. Let's edit it. Let's change it so it's not capital of France. Where did I put the prompt? Was that down the bottom? Let's just change that to that, what is that, Tommy effect again. I have no idea why I came up with that particular phrase there, but that one works. And let's run that again. What is interesting is you can run the same query on a large language model, and you don't always get the same response. That's a peculiarity. Okay, so let's see what happens when it comes back with what is the Tommy effect. So I've got a question as well from somebody on the in the area then. So, do you need to download eSpeak code when running Python using Visual Studio Code? Yes. If you're on a Mac, you might need to do homebrew, install eSpeak as well, eSpeak NG. So this code, this text that's been returned is much better to put through a speech synthesis because it hasn't got any of those kind of non-speakable characters. So although it looks like a very large block of text, we can shorten that down by just telling the prompt to give us a shorter response. So in fact, let's try that. Let's go down to the very bottom. Just like ChatGPT, you can say, please give a single sentence answer. like that. Okay, let's just run that again. See how it finds that one. Is it going to give us quite as large block of text or not? So Goldfinger, that question you was asking about eSpeak, is it installed as part of Python? Do you need to import it? I'll show you how we can go about that. I kind of do this in reverse order. I want to show you the good stuff first and then kind of get to the more complicated stuff kind of secondary to that. So the demo 4 is going to be taking our text to speech, our speech to text, our large language model integration and putting it all together in a single program, which isn't much bigger than the second one, the third one even that we've just used. I just want it to come back and see if it does indeed give us a single sentence answer to this. The other thing we can do while we're waiting for that to come back, if we open up another terminal window, we can do htop and we can just see just how much CPU this is using on this Raspberry Pi. It's using almost every single cycle of CPU that it can to respond, and you can even see that the top running process there is our Ollama model, so that's it's maxing out as much as it can to give us the response. But it's doing all this on device, it's not sending anything into any clouds, doesn't require any internet connectivity. We can run this entirely on our device. There we go, so we've got a single response. It's more than one sentence to be fair, but it is a lot shorter than that very first one. Cool, how cool is this? Right, let's go back to our final demo. So let's go to main.py and let's have a look at this one in a bit more detail. So this is very similar to that third demo program that we created. We've got all the usual kind of imports. I've created a prompt on here which will be included on every single request that we speak. So you can say, you're a helpful assistant, answer the question in a friendly and informative manner. And then we've got a welcome message which is, hello, I'm your virtual assistant, how can I help you today? We've then got that remove emojis, clean up piece. We've got that other clean response, and that just helps just give a more speakable answer. We've then got the details about the VOSC model path, the Ollama path as well. On this one I'm using Tiny Llama rather than DeepSeek, so we can simply just comment out whichever one we want to use. Let's go for the Tiny Llama on this one. We don't actually need that code on there. I was originally using Pi text-to-speech 3. Well, that can get a bit glitchy. It doesn't always finish its sentences, so that's why I've gone and used eSpeak instead, so we can actually comment that out. So the model we're using is the model path we provided there for VOSC. Created our queue, created our callback. We've got our regular recognize speech function that we created before. Query Ollama works in exactly the same way. And then we've got the speak thing, which simply just speaks any text that's passed to it. And then our main code, this is the kind of new bit for the for this particular demo. So it simply says, say something. We then say the welcome message. And then while true, we listened for speech that's been spoken. That's saved in the spoken variable. If there's nothing in spoken, then it'll just carry on going around that loop. If something has been said, it can then say, you said, and then the actual text that it's received back. If we have any of these commands, such as quit, exit, stop, bye, goodbye, or goodbye with a space in the middle, it will then say goodbye and then stop. Otherwise, we will send that response to our the spoken response to our Ollama model, whichever one we've chosen. It'll come back in that response. We then clean that response, get rid of any emojis, and then we speak it. So that's how simple this project is. It's not a massive amount of code, but it's surprising how good it actually is. So let's go back to our Raspberry Pi. Let's get this up and running. So what I'm going to do now is do Python 3 main.py, and I'm going to put the headphones on top of the microphone so you can at least hear what it's kind of saying. And I'm going to try and make sure that we've got the volume on max as well. Okay. I do need to speak, that's the only thing. So when I'm going to speak, I'll just have to grab it back up off my off the microphone. So let's try this. Of course, it's decided to glitch for a second. Let me just see what's going on there. I'm just going to quit both of those windows. Let's just load it up again. So I'm just in the... That is, it's because this is open. I did see this happen last time. So if you change and this stays on screen, you can't then type. So I just need to troubleshoot how to fix that. I think the easiest way is probably just to reboot the Pi actually, so I'm just going to do that because, oh no, it's disappeared now. I can now type. Right, okay. So let's just zoom in a little bit on there, just so you can see what's being said. I need to go into the Thinkman folder. I need to activate my virtual environment. This is what I have to do normally the first time I run this. So then it's bin and activate. And then Python 3 main.py. Okay.
Hello, I am your virtual assistant. How can I help you today?
Tell me a joke. Let's see how good it is at telling jokes. He's thinking about it. So I'm just going to give it a second to tell me a joke.
Where we compete in a mock debate. This week, we decided to put our arguments together for a new twist. The subject: should humans live on Mars? Bill: good question. I have a few ideas, but they all boil down to this: if it's a life-supporting environment, it could work. But let's be realistic and
This
practical.
is a very elaborate
There are
joke.
so many issues we need to address before sending people to Mars. Here are a few that come to mind. Emma: okay, but what about the oxygen? Bill: fake laugh, I'm not a science expert. Emma: but according to NASA, the Martian atmosphere is 95 nitrogen and 4 argon. So we need oxygen. Rachel: size, and there are also environmental problems on Mars.
What?
We have to be mindful of the ecosystem, which can include microbial life forms that could pose a threat to humans. Emma: but how about water? If we're going to live in the desert, we need
Where's
to
the
find
punchline
water,
of this?
and Martian soil is a little on the dry side. Bill: shrug, so, yeah. And with limited resources, we'll have to be resourceful in terms of food, shelter, and even clothes. But don't worry, there will be plenty of opportunities for us to learn about this new world. Rachel: jokingly, that's the spirit. We might find a way to adapt. Bill: exactly. Let's put on our thinking caps and start dreaming up some solutions. In the meantime, let's celebrate our newfound enthusiasm for exploring Mars. As they all laugh.
Goodbye. There we go. Cool. So it's not the best joke teller, and you can see that there was a little bit of a delay there, and we can just have a look at that main.py to see which model we were using there. I think it was the Tiny Llama one. Let me just scroll up and check. So on that one, yes, we were using the Tiny Llama model, so that's a bit smaller, a bit quicker to run. So how did we get all this set up? So I've just shown you the kind of finished article on the Raspberry Pi. How did I actually go about installing all this? So the first thing I would do is I would do git clone https github.com/Kevin McAleer and then Thinkman. I've already got this downloaded, so that would clone the code. There isn't very much code to be installed, to be fair. So if I then go cd Thinkman, let's have a look what we've got in here. And then what I need to do is run the installer. So if I do // and then install sh, it will download the VOS model as if the VOS model doesn't exist. It will do a port audio install, eSpeak install. It will bring up the Docker container that's running Ollama, and it will even install the Ollama models as well. I'll show you the install code because it is actually quite interesting to see how this kind of fits together. So let me just close that window there. So first of all, we say if we don't have that VOS model small, which is the speech recognition model, then it will say it doesn't exist, downloading it. It'll then get that from the source. It'll unzip it. Otherwise, it'll just say it already exists. It'll then say it's VOS models downloaded and extracted, installing port audio dependencies. So then it does a sudo apt update, sudo apt install, libportaudio2, portaudio19 dev, espeakng, and the -y just means install all that without actually prompting the user. It then creates the virtual environments. That's got a bit of a typo there, but ignore that. So installing UV, which is the ultimate virtual environment creation tool. So we do curl and all those parameters there. We get the UV installer. We then run the UV installer. We can then source home local bin env. This just brings in some of the environment variables that we need for running UV for the first time. We can then create a virtual environment, and it does it much quicker using UV than it does if you just do a regular Python code. We can test that out actually. So UV VMV will create the virtual environment. Now, if it already exists, so that's what that file check there does. If it already exists, it'll just skip that. It'll then activate that environment. So source vn bin activate is how we activate the virtual environment. It'll then do a pip install -r for the requirements. We can have a look at that requirements.txt as well to see what is in there. Let me just, why can't I scroll down on there to see where that is? I just need to jump back. So there is a virtual, there's a requirements.txt. I can't see it on there. That's weird. Let me just see ls requirements.txt. Yeah, it does exist. So I don't know why I can't open it on there. Ah, it's because I'm looking in the wrong place, Kevin. That's why. There we go. Requirements.txt. So just VOS, sound device. We don't even need that Python text-to-speech anymore, but that's fine. And requests. So they're all the modules that we pull in there. And using that pip install -r requirements will actually install all those prerequisites. It'll then bring up the Olama, so Docker Compose up. So there's a Docker file. We look in that Docker Compose. That's my my go-to code for bringing up the Docker container. So the only thing that you might need to change in here is the location of. Let me find it. Oh, in fact, I've already given that a variable. So I usually have like the account Kev on my Raspberry Pi. So the user home will be whatever your user account is. So that's where it will store the Olama large language models. And yep, everything else looks fine on there. So it's going to just map some ports and so on, but bring up both Olama and the Olama web user interface. So you can use that as well if you wanted to connect directly to that. Okay, so that's the Docker Compose. And then the last two things will actually connect into that running Docker container. So it'll do Docker exec Olama, which is the name of the image that we're running, and then run deepseek. So Olama run deepseek is the command. Olama run tiny llama. That'll essentially just download that if that doesn't exist on your Raspberry Pi. And it won't do it on the very first time you run that, of course. So that's how we actually get all those things installed on the Raspberry Pi. So it's very, very simple. We just run that. We now do Docker PS. We can see on there we've got Open Web UI, and we also have Olama. So if you wanted to, you could actually connect using your local browser, so local host, and then port 3000, I think it is. And this is Olama Open Web UI. So we can click on the Get Started thing. You can give yourself an account on here. So let's just create an account. Okay. And if we just say, okay, let's go, we can now use Olama like we would normally. So you can see we've got the two models. So Tiny Llama and DeepSeek. If we wanted to install more models, we could go into the admin panel, go to settings and models, and I think we click on that little download button there, and then we can actually type in the name of the models that we would want to download. So I think Phi, for example, is that one. Is it Dolphin Phi? There you go, so it's going to start pulling Phi. I'm going to cancel that just because I don't want it to interrupt the broadband connection that we have running there. But that's kind of how you could do that manually. But you can also do that on here by typing that command. If I just do cat install, if we do that echo and then bracket quotes /by, that will tell the Olama command line to quit. And if we do docker exec or llama run and then fee, oops, oh, done that wrong now. Let me just grab that code. So it's that code there. Copy that and then paste that in again. I just want to show you we could do that. Oh, there we go. And then instead of it being tiny llama, we can just delete that and type in fee. So it's going to pull the fee just like we would, but doing it a command line version rather than pulling it through the web interface. That's just another way of doing it, but that's how that install script works. It has everything you need to get this project up and running on your own Raspberry Pi. So we've looked at DeepSeek, we've looked at Tiny Llama as two different alternative models. You can simply just go into the source code, the main.py, and play around with that. But how cool is that? Simply just plug in. Let me just disconnect the power, and I shall also be able to show you inside how this works. So this is just connected. I've just got a network cable just so that we can see what's going on the screen. You can see we've got a bit of a low voltage warning there. I think I need to give the battery a bit of a charge, but this is actually running on here live as we speak. So if I run our main code again, so Python 3 and then main.py.
Hello, I'm your virtual assistant. How can I help you today?
Where is the capital of France? So then it's going to find what the answer to that is from its own information. So this is quite chunky. Look at the width of that.
France, which is also its official name, is Paris. It is the largest city and the most populous city in France with over 2 million inhabitants as of the 2019 census. The city is divided into several arrondissement districts, each with their own administrative and political functions. The capital's name refers to its status as the seat of government for France, which is called the Chamber Haute High Chamber.
Goodbye.
Au revoir, salamander. See you again soon. So long. Auf Wiedersehen. Adieu. Bonsoir. Bye for now. Bye bye. Auf Wiedersehen.
Stop.
Goodbye.
Cool. So let me show you a couple of other things with this project before we get on to the last bits. So if I open this up, you can see before I opened it a bit like an original Walkman. This isn't actually attached to anything. It just looks like a hinge, but you can see there's the Raspberry Pi inside. If I remove the top, you can see we've got the battery, we've got the Raspberry Pi 5, we've got the M2 hat on there with a NVMe SSD in there as well. You can see I've got the network connections on there, and there's access to be able to charge the battery like that. I put that in there, that will charge the battery up. And it's completely running. You can see if I pull the power out, it's still working fine there. You can see the NVMe lights are flashing away and so on. And if I just push these back on, you can see we have the project kind of proper. So there's the connections, there's the access to the buttons underneath, kind of the screws on the back there. And yeah, it's quite chunky, a bit chunkier than original Walkman. And the other thing is, look at these cool headphones. So Jenny crocheted these. They're really, really cool. They just connect on to the headset to give it that original kind of 1980s look from the original Walkman. Cool, cool. Right, let's jump back over to our slides. So I hope you enjoyed that little demo there. How cool is that? Such a fun project. Definitely try this out if you have a Raspberry Pi and you have a headset. So if you want to join our Discord server, you can jump over to kevsrobots.com/discord and you'll be able to speak to all the amazing people there. So a really vibrant community of people just like yourselves doing kind of cool projects. And if you'll follow me on social media, I'm on all the social medias. So I'm on Threads at KevMcAleer at threads.net. I'm on TikTok at KevMcAleer6. I'm on Instagram at KevMcAleer. I'm on X at KevsMac. I'm on Mastodon at kevsmac at mastodon.social. And I'm also on Blue Sky at kevsmac.bsky.social as well. Cool. And if you want to get your name on the end credits, you can do that by going to kevsrobots.com/coffee. All the information that you need to do that is on there. And let's do that right now for the people who have done exactly that. So over on this side, we have Marie-Louise Mayer bought me 3 coffees last week. Thank you very much for that, Marie. Really do appreciate that. Somebody wanted to be remain anonymous also bought me a coffee. We have an anonymous member. We have Silicon Fiber, Marie TKD. We've got Jeff Johnson, DN Corty, Marlene Brent, and we have Tom. And then over on the YouTube side, we've got Justice, we've got PIUs, we have got Orksrad39, Bert, Marie, Michael. We have Steve, Ford, Bello, Paul, Johnny, Stephen, John Paul, Cassie, Tinkering Rocks, Johnny, and Tom. So thank you all so much for supporting the channel. It means so much to me that you do this. And I can build cool projects just like that one as well. Cool. So the other thing I just wanted to say just before we go back is we do have a project on Kev's Robots that you can follow along with. So if you go to the Robots and Projects, Thinkman has a page all of its own. You can just click on the blog as well if you wish to do that. So we click on that. Of course, it takes its time thinking about that because obviously we're live and obviously it can't just do that quickly, can it? So what we're going to do is just go for Projects /Thinkman. Oh, there we go. It's loaded up anyway. So here we have all the information that you need to download that. So there's the git clone command. There's the software stack, the Python setup, a bit more about the install program. And then if you want to set up the virtual environments, you can use that UV. There's the install script for UV. The installer will do all that for you actually, so you don't really need to worry about that. If you want to know how to install Docker, there's a link on there to the Docker course that tells you how to install Docker. A bit more information about bringing the Docker Compose containers up and how to install DeepSeek and TinyLlama. If you wanted to do that manually, the installer will do all that for you as well. And then there's the, there you go, there's that link to how to install Docker on all the different platforms. So that's nice and simple. And yes, back on here we have all the images of all the different parts. There's the link to the code, and there's the 3D printed models. If you wanted to download those, you can do, and there they kind of are kind of rendered for you. So yes, all available on kevsrobots.com, so definitely go and check that out as well. So at this point in the video, YouTube will be recommending over here another video from the over 420 or 30 videos that we have on the catalogue now. So definitely go and check one of those out. It'll be handpicked by the algorithm just for you. So thank you so much for watching, and I shall see you next time. Bye for now.